Hello and welcome to my presentation about splitting a monolith into microservices at the scale of 20 million requests per second. So this presentation won't be about patterns, how to achieve clean microservice architecture. This presentation will be strongly focused on the performance side of this challenge, so the latency and scale challenges. So before I start with explaining our agenda for today, I will give you a brief explanation of who I am. So my name is Łukasik. I currently work as a senior software engineer and tech lead for RTB House. I have about 6 years of commercial experience as software engineer, and my specialty now is building reliable, scalable systems in Java. Okay. So enough about me. Now let's go to our agenda for today. We'll start with a brief introduction about what RTB House, so the company for which I work for, is, what we do, what challenges we face, what makes it interesting enough to talk about on this conference. Later, I will give you like a really brief explanation of our architecture, so where the monolith which we decided to split is located in our ecosystem. And later, I will tell you about why we decided for splitting this monolith. So what was wrong with it, why it was worth this effort. Later, we'll go through what constraints or non-functional requirements we have established for our whole project of extracting microservices and what was our initial idea for the design of this migration. Later, I think the most interesting part of that would be like the practical challenges and solutions which we encountered during our project. And so we'll go through load balancing at scale, overhead of having huge amount of small requests, impact on garbage collector on the service's latency, and also we'll touch the problem of ensuring system resilience. Finally, we will talk about what architecture we have achieved in the end and what benefits we managed to achieve from that. Okay, so first I will provide you some context about what RTB House is. To explain what our company does, I have to first explain what real-time bidding is. So each time you visit some kind of a news page, for instance, like ONET, BBC, or something like that, you often see a lot of ads. Some of them are personalized based on the items you browsed previously in some e-commerce platforms, or it can be personalized based on the content of the web page. So the whole process of deciding which ad will be displayed for the user and displaying this ad is much more complicated than it may seem. So actually, this process is usually realized through real-time bidding auctions. In real-time bidding auctions, we basically have two parties involved. That's like a simplified version of this whole ecosystem because in reality it can be more complex. So first party is supply-side party. So it's the party with which the publisher who wants to display an ad signs a contract with. And this publisher, like Google ADX, I think that's the most famous one, organize a real-time bidding auction to decide who will display an ad and what type of ad will be displayed. And we also have demand-side parties here, like our company RTB House, which connect to these supply sides like Google ADX and buy this advertising space to display personalized ads. Okay, so our responsibility in this whole ecosystem is to evaluate bid request which we receive, because this request to display an ad is called bid request. And we want to evaluate it, tell if we want to buy this space and how much we are willing to pay for this space. And later, if we win an auction, we have to display this ad to the user. And later we can get profits from it by displaying ads or we measuring how much clicks we get on this ad and so on. Okay, so as you probably can imagine, the scale of this system has to be quite large because there are a lot of ads displayed in the internet every second, and there are a lot of real-time bidding auctions happening every second. Our platform currently handles about 20 million bid requests each second. And we do not win like all of them. We win only a small fraction of them, but it's still like a big amount of auctions. Another interesting challenge here apart from like distinguish this valuable bit request from invaluable bit request in our bit stream is the latency requirements which we have. Because those real-time bidding auctions have to happen in real time, basically, so the latency requirements which we have here are pretty strict. In general, we can say we have around 60 milliseconds to respond to such auction but it also includes the round trip, so all the network overhead and so on. It can vary and by multiple factors, but just to give you an example of with what we have to deal with here. Okay, so now let's go to a really general overview of our architecture. So basically, we have a user device. So someone wants to display this BBC News or ONET or something like that. And this publisher website has an agreement with a supply-side provider, so supply-side platform, which then organize this real-time bidding auction. So this provider calls our bidding services and he sends an offer to display this ad, so this bid request. Then our platform has to evaluate each request. The component which is responsible for that is a bidding service. We have multiple data centers all over around the world to handle this traffic meeting our latency requirements. So this bidding application has to respond really fast. So this application has to be like highly optimized for latency because we want to evaluate, we want to like learn more as possible about this request in a short duration of time in order to bid efficiently. So this monolithic application of bidding service has to consult the profiles database to get the information what we know about this user and database of context of a URL on which we are bidding, because when we are bidding on a site about cats, probably we want to advertise cat food because someone has a cat. That's also relevant information for us. We also needs a lot of static resources loaded inside our application because, for instance, we get a user IP address, and from this user IP address, we want to tell in which country, region, and city this user is located. Okay. Later, if we win such auction, we have another like pipeline here, which is responsible for delivering this ad. So this pipeline doesn't have to be so optimized because latency requirements then and the scale are not so strict, but also that's like an important part of our architecture. So this whole presentation will be about this bidding service. So how we managed to split this bidding service at the scale of 20 million requests per second. Okay, so first we will go through our motivation. So why we have decided to split this monolith. So in general, the memory in each application is limited. So we have limited RAM on our servers, and we cannot usually easily extend that because we have physical machines, its hardware is expensive, so we have to meet our constraints here. As I already mentioned, our bidding application loads a lot of static resources inside its memory. For instance, this geo database, which is used for mapping between IP address and the country, region, and so on. If we have multiple features like this, easily we can allocate a lot of memory inside this application. Also, sometimes we want to store some in-memory caches, which help us to speed up some computations. Okay, so that's one motivation, that we have problems with memory on our servers. Other thing is that when multiple teams have their code inside a single application, it becomes hard to orchestrate everything because we have to synchronize deployments, it's hard to establish clear interfaces, and so on. Other thing, maybe not so obvious, is that when we have multiple instances of some in-memory cache, then it's much less efficient when we have fewer instances of this in-memory cache, because there are like less times we have to compute the same thing. It's also hard to implement. Sticky sessions when we have only one front application. We cannot like partition our traffic to. So, for instance, we could if we had two services, we could send the same user always to the same instance of the service, and then we can cache some computation results specific for this user on this machine without using some external cache. So it could be also beneficial to have this possibility. Okay, so now I will go through the requirements which we have established and also the initial design which we come up with here. Okay, so let's start with those non-functional requirements. So first requirement is latency. As I already mentioned, our bidding service has quite strict latency requirements. So if we wanted to extract some microservices from it, we have to determine how much latency we can add, because calling an external service always will add some latency. But we wanted to learn how much latency we can add in order not to break anything. So to do that, we created an A/B test. So we basically divided the group of users who access our platforms into multiple groups. To each group, we added different artificial latency, and we later measured the business performance for each group of users, because it's quite simple to measure that. In our case, we can measure clicks, for instance, for this group, and for some group of users, observe that the total number of clicks during some time period is lower than for the others, so then we can conclude that something went wrong here. Okay, and from our research, we determined that we can increase the latency on about 7 milliseconds. So that was our constraint for this migration. Higher latency would decrease the business performance for some requests, so that was something that we wanted to avoid here. Okay. So now about scale. As I already mentioned, we handle more than 20 million requests per second globally. If we want to have some margin here, because those number of requests is rising and rising, we want our system to be able to handle about 25 million requests per second globally. But if we want to call, for instance, 3 microservices during processing of each bid request, then it's get multiplied. So we have 75 million requests per second flowing through our systems. So that's a big amount of requests. The other thing is the resiliency, because when we extract some microservices, we have a problem that they are not present in case of Monolith. So we have to take care of the deployment, the downtime of microservices, some transient errors, latency spikes, and so on. These problems are not present if we have like a single application with a single runtime, but occur when we need to call some external service during processing of our request. Okay. So here, like a brief explanation, what services were extracted from our monolith. So in general, we decided to extract 3 microservices from our monolith. And a service that is responsible for parsing the URL context. So basically the server which accepts URL and tells us what we know about the content of this URL. So is it about cats, is it about sport, or something like that. Why? Because there's a quite big cache on site of this service, which could be further extended after this migration. Other service is the gRPC resolver, which would be the service responsible for extracting user geolocation from the IP address, basically. As I already mentioned, the geodatabase needed for that is quite big, so it was a good candidate to extract. Third one would be user agent analyzer, so basically a service responsible for parsing the information from the user agent. That may not be so obvious why it needs a lot of memory, but parsing user agent when we have strict latency requirements becomes a really heavy operation, and we want to cache as much as possible. So we have decided also to extract it as separate microservices in order to be able to increase this cache size. Okay, so now let's see the high-level design of the migration from which we started. So basically, we have decided to separate the process of processing each bid request into 3 stages. So a stage when bid request is parsed, because it usually comes to us in a SSP-specific format. Later, we created this enrichment phase when we want to call external resources to get more features about our request. And then we have the evaluation phase where we run machine learning models, some policies, and so on in order to evaluate if this bid request is valuable or not. And we also decided to extract 3 microservices, so we set up 3 different microservices called via gRPC. Okay. So now let's go to, I think, the most interesting part of that. So these practical challenges and solutions related to this whole migration. Okay. So the first problem which we encountered was a problem with load balancing, because our initial approach involved using a centralized load balancer for handling all this traffic. We used this approach because we had experience with centralized load balancer. We didn't have experience with client-side load balancing, so we wanted to do it as simple as possible, not to learn new things when it's not necessary here. So in order to check if this approach would be efficient here, we set up an experiment. So we set up a test cluster with 2 HA proxy instances, and we checked what percentage of the traffic from our Amsterdam data center we can handle with this cluster of HA proxy. And the results of this test were quite alarming here, because it turned out that with 2 instances, we could only handle 3 to 4% of the traffic from only 1 data center. And if we do the math, it will turn out that we would need something between 50 and 70 instances in only 1 data center of a load balancer to handle the whole volume of the traffic. So basically, it would be too much, because all of this processing power which we use for those load balancer is basically wasted. It's something that we have to add extra, which is an extra cost for our project, and this number was too big to accept. So the easy solution for that was to implement client-side load balancing. Now, easy it sounds, but there are significant challenges that come with implementing client-side load balancing here. So in our approach, we decided to use a simple round-robin policy, because we ensured that all the clusters of our microservices are homogeneous, that all the machines there are the same. So round-robin client-side load balancing seemed like a good choice here. We also had to take care of the service registry. We didn't have any standardized approach for managing service registry. So we used the simplest approach as possible. So we just created a DNS domain for all of the instances that serve the specific service, and a job which maintains this domain based on Puppet information and also health checking the containers. Okay, and other challenge which we had to solve here, fortunately, we used gRPC health checking protocol here to manage the health checks. So we ended up with an architecture like that, shown on this diagram, when we have this bidding service which consult our DNS-based service registry, and later we run health checks on each of those services and send traffic to the healthy instances. And the interesting thing here is how this health checking protocol works in case of gRPC, because it's not the usual health checking protocol here, because client-side load balancer don't probe the servers constantly. Instead, in standard gRPC health checking protocol, we used streams, because gRPC supports basically 2 types of requests. Either it's a unary call, so like a regular call with a single response, or we can open a persistent stream and stream data through it. In gRPC, this client-side health checking protocol relies on streaming. So basically what client-side load balancer does, it opens a stream to each of the backend service and listens for the health check updates. So you have a concept of this on the diagram on this slide. Okay, so but there is a maybe not so obvious pitfall with this protocol, which we encountered on production. And so basically this protocol is based on the statuses pushed from the server to the clients. We can easily imagine that it might happen that the server stops to be healthy, so for instance, out-of-memory errors happens. The server is in undefined state. It basically hangs. It's enabled to process the request, but it fails to push its unhealthy status to all clients. In this case, the client-side load balancer still assume that this backend is healthy, so they still send the traffic to this instance. That can be a problem which happened in our production environment, which could be mitigated by handling of timeouts or external probing of backend instances and removing them from service registry. Okay, so now let's go to other challenge which we encountered. I think the most interesting one here. So in our initial approach, we assumed that we will send a separate unary call for each bid request to all three microservices. And we wanted to check if this solution will be possible, how much instances we would need. So we deployed again a test cluster of our microservices. We used this client-side load balancing, which I have described. And we checked how much percentage of the production traffic could be handled by this setup. It turned out that by these 7 instances, we could handle about 8 to 10% of the production traffic in our Amsterdam data center with a reasonable CPU reserve. If we do the math again, it will turn out that we would need 70 to 90 instances of each microservice in this AMS data center, and we have 4 data centers all in other parts of the world. So in total, it would be a huge number of instances for those microservices. We started to investigate that, why it might happen, why we need so many instances. So we used, I think, quite common tool, Async Profiler, to shoot a CPU flame graph of our microservices. And it turned out that if we check on what CPU spends actually time, that it will turn out that 20% of CPU time is actually spent on the business logic and 80% is spent on other overhead. So garbage collection, thread pool dispatching, handling TCP, and so on. So it's a huge waste of CPU resources and a huge downgrade when we extract microservices when it comes to efficiency. Okay, so we started to think how we could address that. So our first approach involved replacing this gRPC unary call with gRPC streaming. So basically, we created a pool of gRPC streams inside each bidding service, and we started to push our requests and accept responses through persistent gRPC streams. We thought that it could reduce this overhead because with having separate requests for every call, there is an overhead of sending metadata, headers, computing load balancing, and so on. And we thought that here it would be more efficiently handled. It turned out that indeed it can increase the overall performance of our system, but it could only reduce the number of instances needed by around 33%. It was still not good enough for us. It still was a huge number of instances needed. And also this solution would be hard to maintain because it would involve manually mapping between request and response, because we have persistent stream. We don't have an implicit context of a request. So we just push data through one pipe and accept data through other pipe. So we could match manually those requests and response. Okay, so far so good. So now let's go to how we solved that. So our solution here for this problem was based on batching. So we thought that if the overhead is so big, maybe we can reduce the number of requests and send a fewer number of requests, but bigger, because usually the overhead comes from the number of requests and not from their size. And it turned to be true. We implemented a batching mechanism that assembles a batch of 10 requests and flushes the batch of 10 requests before calling the microservice. And it allowed us to reduce the number of instances around 3 times. So basically it works like this. So we have multiple request processing threads, each processing its own bid request, and they, instead of calling microservice directly, then they push their request to the batching buffer. So this batching buffer basically works as a queue. It assembles a whole batch requests before sending them, and it pushes a whole batch to a microservice. Using this approach, we have 10 times smaller number of requests, and also, as we learned from a flame graph shoot after that, much lower overhead. So implementing this batching allowed us to save a lot of CPU resources, because here 60% of the CPU time on microservice side are spent on actual business logic and not on the overhead. Okay, so we managed to reduce the number of microservice instances needed to a reasonable amount. So it was a success here. Later, we had another challenge, because with batching there comes a trade-off. If we batch the request and we have strict latency requirements, this additional latency is introduced for batching, and also processing of a batch request is longer than processing a single request. So we had another problem here. Apart from that, we observed that if we redirect some amount of production traffic to our microservices and measure the latency distribution of their response times, then we observe a significant tail latency here. So like you can see on these charts here, P99 is really high. So if we had a constraint of 7 milliseconds, then for P99 it's 21 millisecond latency. So it was too much to accept. It would mean that this 1% of request would be for sure timeouted and won't be able to participate in the auction. So it won't be good. So it would reduce our profit. Our first approach here in general involved, it turned out that the problem stems from garbage collector which we used. So in our initial approach involved using G1 garbage collector in all our services, because again we had experience with G1, all our services use G1, so let's again use G1. We tried to tune it in order to reduce the pauses which are introduced and the tail latency in which it results, but those attempts turned out to be inefficient. Okay, so the approach here which worked for us in the end was using ZGC instead of G1 garbage collector. It allowed us to significantly reduce the tail latency. If we compare this distribution with this distribution, we see that P99 is significantly reduced. The average latency, though, is increased. So in average, our latency increased a bit, but we reduced the tail latency. Also, the memory consumption of our microservices was significantly higher, because ZGC has higher memory overhead than G1. In general, if we compare those two garbage collectors, it will turn out that ZGC is really good at work which requires really low latency. So, as in our case, we have strict latency requirements, so ZGC can be a good choice, but it's also a trade-off. So it's not good for everything, because in general, the throughput which you can achieve with ZGC can be lower than in case of G1. And also, the memory overhead of this garbage collector can be higher. So we have to be careful when making some decision that's not always ZGC would be better than G1. Okay, so we managed to go through the challenges related to load balancing, batching, and also this tail latency thing. So now one last thing is system resiliency. So we had to think how to ensure that our system will be stable in case of deployments of microservices, sudden failures of them, sudden latency spikes, and in case when some transient errors occur. So basically we implemented two different mechanisms here. So one is cooldown period. So before we turn off each microservice, we report this as unhealthy to all client-side load balancers, and then we wait for some time before we actually stop the container. So it allows us to propagate this information to all clients that the service is unavailable before it really gets unavailable. This was easy one. The hardest was to ensure that if we have some sudden failure of a microservice or some latency spike, the performance is still stable. So we used interesting mechanism in gRPC, which is maybe not so bound to gRPC, but it has like well support in gRPC client library. It's hedging. So basically, it's quite similar to retries, but in regular retries, we wait for the answer. So we retry when we see a failure from the server. In hedging, we do not always wait for the response from the server. We could send our request before the response arrives from the first attempt to send this request. In this way, we could address some latency spikes because we can retry a request even before it's really timeouted. So we could send a second attempt, for instance, 2 milliseconds after the first one is sent, and then we use the response which comes back first. So we had basically 2 requests active at a time. So it could really it is like good approach when we have like strict latency requirements. We want a stable tail latency, and and also with hedging we could implement like regular retry mechanism. So it also allowed us to handle transient errors from microservices and things like that. Okay. One interesting thing about hedging is that you can easily imagine that if we send a second attempt after, for instance, 2 milliseconds, it might happen that in a scenario when our system gets overloaded, we will overload it even more because our system, the latency is increased because we lack compute power, and our clients start to send even more requests. So then our system will become even more overloaded. So that can be dangerous for our infrastructure, and it is a thing that we usually want to avoid. So in gRPC hedging implementation, we also have a nice support for that because we have out-of-the-box hedging throttling mechanism, which uses token bucket-like algorithm here, which measures the overall health of each backend instance. So it measures if the instance of the backend is not overloaded, and if it gets overloaded, it not disallows further hedging attempts to happen. Also, the feature which we didn't use, but is possible in gRPC, server can also manually send pushback metadata in order to prevent hedging attempts to being sent from the clients. Okay, so now let's go to the final architecture which we managed to achieve and the final benefits. Okay, so in the end, we landed with an architecture when we have bid request processing split into 3 phases. So bid request parsing phase, this external data fetching phase, and bid request evaluation phase. In this external data fetching phase, before we send requests to actual microservices, we put our requests into batching buffers. For each microservice, we have a separate batching buffer, and after the data is put into buffer, we have ticker mechanism that flushes this data to each microservice. After the data is processed by the microservice, so these batch requests are processed, the threads which were waiting for those requests are notified, and the request processing in this bidding service can be resumed. We also used ZGC, garbage collector, for our microservices. We used hedging functionality from gRPC in order to improve our system resilience. Okay, so the benefits which we managed to achieve here are we managed to free approximately 15 gigabytes of RAM from the bidding service, which unlocked us the possibility of adding new features to our bidding service. We also improved the efficiency of in-memory caching because we got fewer instances of a service. Because if a cache was on each bidding service instance, which is a lot of instances, about 1,000 in one DC, then if we move to 28 instances of a service inside one DC, we have fewer instances of a cache. And also this cache is larger because we don't have so strict memory requirements if this service runs separately. So it improved the cache performance, it improved the hit ratio, and allowed us to save some computational resources, which buffered really this overhead which we added by sending TCP requests over the network. And also one thing which is, I think, even more important, that we paved a way for any future migration. So we can split our monolith even further than extracting those 3 microservices in the future. And we already have a framework how to do it. So then that's this, like, for me, an important artifact which we have from this migration. Okay, so I see that we finished a bit earlier than I expected, so we have a lot of time for questions now. Okay.
Why use in-memory instance instead of some kind of shared cache like Redis cache?
Okay. Okay, so when we use like in-memory cache, we save a round trip to this external cache. So that's one thing. But we have like a round trip to microservice here. Other thing. We also have to like maintain this separate cache, have machines for that. So it is like an overhead of maintaining a separate cache for that. I think it was like behind those decisions. Yeah, there.
I was wondering, because you use gRPC batching, so which makes effectively asynchronous communication between your services, would using Kafka be a simpler solution for your need, or is it the latency is a constraint here? Or?
So in general, we didn't want to use like asynchronous approach as with Kafka, because we had like this strict latency requirement. So this round trip to a microservice had to fit in 7 milliseconds, which would be, don't want to say that impossible with Kafka, but I think it would be much harder to achieve this with Kafka than it with our custom approach to batching and using gRPC. Okay.
Thanks. So one thing intrigued me about that gRPC health check.
Mm-hmm.
So you said that it actually is not foolproof.
Yes, it's not.
So does it make sense to use it at all?
It makes sense when we implement additional mitigations to solve the problems. So if you have this external probing, which checks, which sends health checks to those containers and removes from service registry when it sees unhealthy instance, then in some latency we will remove this instance from the health check mechanism. If we also have good timeout handling, for instance, with this hedging approach which we used, then our system can tolerate this faulty microservice for some duration of the time, and then it will be removed by our prober. So this approach in general is fault-proof, but the health checking protocol alone is not.
I just got a bit surprised at the beginning when you showed that you're using gRPC to multiple instances to geo-IP database, read from the database as I understood. So what is the size of your geo-IP database? Like, is it not like 10 gigabytes?
It's like 10 gigabytes, right?
So why not in-memory lookup table and that's it?
In-memory lookup table, because it is precisely what we done in the end. So we extracted a separate microservice which maintains it in memory as some kind of lookup table, because it's not so simple just to, for instance, store a lookup table in some external cache and look for that to map IP address to a country. The service is quite a bit more elaborated, because it might not accept only IP address, but it might accept, for instance, a region, and it has to like conclude the country from it. So there are like multiple cases here. So it's not such a simple lookup table. So we decided that it's better to extract it as a separate service than using an external cache.
Okay, I have a question. Do you use
like coding techniques as in high trading companies? Like optimize the code in the same way, or do you use more like standard approach, so to speak?
We use more standard approach, we would say. We don't use OpenHFT library or things like that, but we try to write our code as optimal as possible. For instance, we avoid streams in our critical paths because we know that streams are not so efficient in Java when you have like strict requirements. So we try to write code as efficient as possible, but we don't use so like low-level techniques here. But we might in the future. That's the state for now.
You told that you use Java. Why you choose Java instead of Go or Python?
Okay, so basically our bidding service is like, for historical reasons, is written in Java. Those modules which we wanted to extract are also written in Java, and their logic. From this presentation, it might seem that it's like easy. They're like simple lookup tables or something like that, but like in real case, they're like much more complicated. There are some edge cases, so like rewriting them to some other technology would be additional overhead for the project.
Can you get back to hedging schema?
Yes?
Okay, so here, aren't you afraid that at some point, if a few servers will go down and the hedging will overflow other servers, causing like a collapse of all the system?
So yes, it is possible with hedging, but we have this hedging throttling mechanism, which disallows hedging attempts when it sees that server to which it starts sending traffic has increased, starts to have problems. So it responds with timeouts, it responds with errors, and so on. Also, we could implement on server a mechanism which monitors its CPU consumption and send this pushback metadata on responses that it is not willing to accept any further hedging attempts.
I didn't get that. If after that shift to batching your requests, have you stayed with that gRPC streaming to each microservice, or you?
Okay, yeah, sure. So here we resigned from using gRPC streaming because, as I told on this slide, this approach with streaming is hard to maintain because it's much more complex in the code. There's like a huge possibility to do something wrong, to lose some messages. So we just use unary calls, but with batched requests because it was like simple and efficient enough to be accepted. This number, yeah. So we performed tests where we have done like obvious trade-off between latency and the number of requests that are batched together in one request. So we concluded that the number of 10 is like a reasonable trade-off between this latency thing and efficiency.
In Kafka, you have exactly that stuff. So we have like a linger MS, which tells you like, okay, it's 5 milliseconds until you make a batch or you pick up a batch size, right? So like in my history, we did modify those two things with Kafka, obviously, but it seems like similar stuff for you. Like you can actually measure it and then change them, because in our case, similar to yours, like, you know, P95 was obviously bigger because we increased the linger a little bit too much, but P99 was actually perfect, right? So was wondering why you didn't choose this path to like have these two parameters to actually tune this rather, but maybe you did, but you just said 10 messages.
Yes, I've like oversimplified maybe a bit this mechanism here, because actually we did not like set the number to be strict 10. We just set the maximum time that a message can spend in a buffer because before it's flashed, and like from this batching delay, which how we called it, this 10 mile, it implies this 10 requests per batch. Basically, it works like this. But the tail latency here, which we had problems with, was like result on the processing on the microservice side.
Could you share your favorite Java optimization tricks?
Favorite Java optimization tricks? Wow, that's a tricky question, to be honest. Like in general, when we write code which has strict latency requirements, we avoid streams because they generate additional overhead. Oh, okay. So maybe one trick which I also would like to implement is I think on the one presentation before this one, it was already mentioned that if we have a list, for instance, list of longs, we could replace this list with a list of primitive longs, so a native implementation, which would have like a lower memory overhead and would be also fewer objects. So that might be other optimization. But I'm not really so prepared for this question, so maybe we can talk after the presentation.
So a follow-up question. So you relied heavily on profiling, and you mentioned you have strict latency requirements on production. So how did you do your profiling? Do you have like a test environment that you try to reproduce the production load? Do you do your profiling on production? What tools are you using for that?
So we did profiling on production. It's somewhat stems from what type of requirements do we have, because in our business it's not usually a problem if we fail 5% of requests for like 10 minutes. It's not such a big deal. It's not also a problem if we won't bid for 15 minutes because we are usually limited by the budget which we want to spend on our advertising campaigns. So the guarantees that our platform has to give are a bit different than in case of most systems, because we are invisible for the end customers. We are just a party in the auction. So if you don't bid for some duration of time, and later we'll spend the budget, nobody will notice really, because it would be like a bit the same for the company. Okay, any questions?